In today's lecture, we saw two apparently disconnected topics. We'll see that they're not so disconnected after all. First one is a description of what an isometry in a finite dimensional real inner product space looks like. And what we saw is that an isometry can be described as follows. There is an orthonormal basis, B, such that, so there's a strong geometric component here, so we can see orthonormal directions where this isometry is working. And some planes are being rotated by a certain angle, theta. For each different plane, it can be a different theta. Some directions are being simply preserved, and in some directions there are reflections. And this is what isometries can do. And this is very well aligned with our intuition of what an isometry is. An isometry will get an object like this and send it to an object like this. In case it's just a reflection, it could include some rotation, etc. This is different from normal operators. It's a particular case of normal operators. In case of normal operators, there is a rotation, and besides the rotation, there is multiplication by some scalar. So we can write this block here, a minus b, ba, as some rotation times some number here, some positive number, which is also a scaling factor. So not only you rotate, but you also stretch each of those planes. And in some lines, you also stretch them, or you reflect them and stretch as well. So we can multiply each of these blocks by a positive number in case of a normal operator. The other topic we saw today is how to go from complex diagonalizations, that's when TC can be diagonalized, to real 2x2 block diagonalization. That's the main part of the second part of the lecture. And why are these two things apparently unrelated? Well, that's because to understand what real isometries look like, we simply used the general form for what a normal operator would look like, and we combine it with the main property of what is an isometry. An isometry, it is normal, which makes its matrix implies that its matrix has to be in this form for some orthonormal basis, but also it preserves norm. And preserving norm here means we don't have these stretching factors. We only have rotations, some directions that are kept unchanged, and some reflections. And however, here, to get this form, this general form for normal operators, we used the very same principle that we have here, which is when we have a non-real eigenvalue for the complexification of the operator t, complexification of t, then to that non-real eigenvalue, we can find a complex eigenvector. We can split the real and imaginary part of that complex eigenvector and see that these two vectors, they are related like this. Their span, as real vectors, their span is invariant under the real operator, and restricted to their span, the operator will have a matrix that looks like this. Whereas for the real eigenvalues, well, if you have a real eigenvalue, you take an eigenvector, at least one of the two parts is non-zero, either the real part or the imaginary part, or both, and in any case, both of them are in the eigenspace of that eigenvalue, and one of them is an eigenvector, the other one might be zero. If it's non-zero, it is also an eigenvector with respect to the very same eigenvalue, real A. This is for the real eigenvalues. So see, these two topics, they're not completely unrelated. They are related through this same principle here, this underlying principle, which was not so apparent in the first part of the lecture because it was already built in on what it was built on the top of, which is the block matrix for normal operators. Finally, since 2x2 block diagonalization is for operators whose complexification is diagonalizable, what happens when the complexification is not diagonalizable? Well then, in that case, it has a Jordan form. That's a theorem. If any complex operator can be put in Jordan form. And in this case, using the same principle that we have here, we can get the analogous to this number if lambda is the number a plus ib, and this is a repeated eigenvalue. That's exactly when we get some non-trivial Jordan blocks. That's when we have an eigenvalue with multiplicity, algebraic multiplicity larger than the geometric multiplicity. So these two eigenvalues, they're the same. There's some a plus ib, like this. And of course, then their conjugates will also be the same, will be repeated eigenvalues. And in that case, using the same procedure that we have here, decoupling first here the eigenvector, and then the generalized eigenvector that is mapped back to that eigenvector in the thread, we get this very interesting and surprising analog of what is the Jordan form for complex. When it's real, it becomes like this. Instead of having little ones on the top of complex non-real numbers, we have little identities on the top of 2x2 blocks that are related to these complex non-real eigenvectors. And all this part of the lecture was built on the top of what is the properties, what it means for a number to be an eigenvalue or for a vector to be an eigenvector of the operator T and its complexification. That's for this part here of this second part of the lecture. And to get the Jordan basis, we just apply first the procedure for complex Jordan basis, and then we group eigenvectors and generalized eigenvectors as their threads, and we only consider the threads for the eigenvalues lambda that have positive imaginary part. For the negative imaginary part, we throw that away, and this will appear naturally when we split the eigenvectors into their real and imaginary parts. Some students pointed out that the same procedure that applied to the complex number gives a Jordan form. If we do this real and complex separation here of splitting eigenvalues and taking imaginary part, then real part, it gives us the same procedure and it gives us the real Jordan form. I have to say I agree with that. And although it is quite amazing, we can try to understand it a little bit. So if we have here, this is what would correspond to a Jordan block, a complex Jordan block. And if vectors u1 plus iv1 and u2 plus iv2 are related like this, then with respect to an operator, a complex operator that is the complexification of a real operator, then the same thing will happen for the conjugates. So we have two blocks like this. So I mean, these blocks, they come in pairs. And this identity here is related to existence of this block. But we can also expand what is the real part and imaginary part of this operator and match with what this eigenvalue, this complex non-real eigenvalue lambda will give us. And this, looking at the imaginary part first and then the real part, this gives us exactly these blocks here. So these two equations here, they are expressed by the first and second column of these two blocks. Well, in the third block here, this block is less important. It's just the fact that u2 plus iv2 in this example forms an eigenvector. So this explains why we can reaccommodate the real and imaginary parts of vectors whose matrix for the operator would look like this. By taking the imaginary part first and real part and writing them in the correct order will give us a nice block like this. I hope this helps clarify. I'd like to point out that what we are doing here is not exactly diagonalization of real operators. First of all, because we cannot always do that. We can only do that when the original operator is already diagonalizable, simply by applying this trick to each element in this basis of complex eigenvectors one by one. And moreover, it's not exactly diagonalization, because what we get is not a diagonal matrix, it's a block diagonal matrix. It's not as good, not even close. I would also like to point out that what we're doing here is not that we're changing a matrix to a normal matrix. We do not have that power. The matrix was normal from, first of all, it's operators we're working with, but let's agree that matrix and operators are the same thing in the end of the day. But we don't change it to normal. It was normal before. If it had not been normal before, we could never possibly make it normal unless we cheated. But of course, it only makes sense to talk about normality, adjoint, etc. if we use orthonormal change of basis. So what we did here is not changing a matrix to a normal matrix. We do not have that power. Also, some people may have the impression that any 2x2 matrix is a rotation, and that's definitely not true. It couldn't be further from being true. Very few matrices happen to be normal, and among those which are normal, very few happen to be just a rotation. Normal 2x2 matrices, they have two aspects. They rotate and they also stretch. vectors. And some people may have the impression that an isometry, an operator is an isometry if the eigenvalues are plus or minus 1, and this is incorrect in both directions. In one direction, here is a matrix, and if you think this matrix is an operator with respect to some orthonormal basis, the eigenvalues are plus or minus 1. In fact, the eigenvalue here is 1, and this is not an isometry. And conversely, we can look here what isometries look like. It has plus 1 and minus 1, yes indeed, but it also has rotation, and with an extra degree of freedom, which is the choice of which directions will be rotated, preserved, and reflected. Now, many of us may be wondering why we are doing this. Why do we want to write operators in this form? I would say it is interesting, at least, and there's at least the aesthetical aspect that we have a real equivalent to a Jordan form, even if this is not technically not Jordan, because this is not 1 and this is not diagonal. We have elements below the diagonal, but we can write any real operator with the smallest possible number of links between the different dimensions of the space. And we are interested in writing linear operators in the simplest form, and this is one of them when it's a Jordan form, or the most frequent case is when it actually the complexification can be diagonalized, so it is a block diagonal with blocks that look like this. Finally, some of us still find it unclear what is this relation between a complex vector being an eigenvector and these two real and imaginary parts being related to each other in this intriguing way, and this relation being still unclear. Well, for that, we can say that it is in the very nature of complex non-real eigenvalues that the imaginary part and real part of eigenvectors are entangled. They are related to each other, because that's exactly what it means when you multiply a vector, by a number that has non-zero imaginary part. It means these coordinates, they will start to mix together and blend together. So these two vectors, they are related, and it is hard to separate them. So what we do is we describe them in terms of one the other, or we describe how the operator acts on them in terms of one the other, in a way that we can ignore the rest of the space, meaning that the span of these two vectors is invariant under the operator. These were the closing remarks for our lecture 20. I hope they are helpful.